So we'll get started by just sort of going over some high-level concepts related to performance monitoring. So there's sort of two ways in general that you can go about collecting data about the performance of your program. The first of these is direct performance observation. And the idea here is that events that occur during the execution of your program are directly exposed as events, such as we have entered a particular region of the code that I care about, and then as an additional event, we've exited a region of code that I care about. We record in one of several different formats the fact that that has occurred and some metadata about that event. Now, what we mean by direct in this case is that we are directly instrumenting the program code. We're inserting probes into your code in order to say something that has just executed is an event that I care about at a definite place in our code. The event measurement then is performance data about that plus the context, which is where the event occurs. And so in order to do this, we instrument your code. We take either your code itself if we're doing source instrumentation, or we take sort of an intermediate output of your code from the compiler if we're doing compiler-based instrumentation, and we modify your code to explicitly trigger a measurement at the beginning or end of functions or regions of interest. This tends to give us the most detailed information possible about the performance of this region because we definitely know that some region of interest has started here and has stopped here. But it has the downside of having an unequally distributed overhead in that our shorter running functions, which are generally going to be ones that we care about less, are going to have a larger percentage of overhead because there is sort of a constant cost of each instrumentation point. Additionally, we need to process the source code going into it in order to insert these instrumentation points into your code. And Tau has several different ways of doing this. We can do source instrumentation where we parse your source code, modify it by inserting calls to Tau's instrumentation API, and then compile it and link against Tau. We can also have the compiler insert the instrumentation for us, and then we can also sort of after the fact of compilation, we can parse your binary and insert instrumentation as sort of assembly language machine code insertions into the binary itself using binary rewriting. So the other central way that we can collect performance data is indirect performance observation. Here we do not instrument code directly. Instead, we periodically interrupt code execution, which can be triggered typically by just some amount of time passing, but can also be triggered by different events related to hardware performance counters that some number of hardware events have occurred. We query the execution state and measure the execution state indirectly by observing what it happens to be doing at the time that we interrupted it, rather than direct instrumentation of specific events. So the idea here is we periodically interrupt your program, record the program counter. We don't need to modify your program at all in order to do this. You just compile with debug symbols for address resolution. And the sort of fundamental thing that is good about this is that you as the user can control the trade-off between overhead and accuracy. If you decide to sample less often in order to get lower overhead at the expense of knowing less about what your program, knowing less precisely what your program was doing at any particular time, and this distributes the overhead evenly. So we have direct and indirect approaches to measurement. There's also, once we take the measurements, there's a question of at what level of granularity we store the results of that measurement. So the two central techniques that we have here are profiling, which aggregates all of the data for calls to particular regions of interest together, such as functions, and gives you summary statistics about that, but does not retain data about individual calls. At the other extreme, we have tracing, which shows when events take place on a timeline. So we individually record, for example, in each entry and exit to a function as a separate event with a timestamp associated with it. Within the realm of profiles, there's sort of a continuum between profiling and tracing that stores more and more data, giving you a better ability to understand what your program is doing at the expense of using more space to store the data. For example, our sort of basic profile is just a flat profile, which is just this function was called this number of times, and on average you spent this amount of time in it. We can also do what are called call path profiles, which is where we sort of disaggregate that and separate out calls to functions based on along what call path you reached that function. So if function foo is called by F1 and F2, that those would be two separate events in our profile. We can also do phase-based profilings, where if sort of as the application developer, you know that, for example, like you have an initialization phase of your application, and then you have iterations of different, within which there are computations of different types, such that your application sort of naturally decomposes into phases. You can sort of manually insert instrumentation that will result in events being measured specific to a phase, so that you can, for example, look at separate iterations separately if you want to see, like, for example, how the behavior of your application evolves over the course of its execution. And sort of in your decision-making process as to what of these you're going to collect, you're just sort of having to worry about a trade-off between the overhead of collecting the data and the amount of data that is stored and the precision with which the data tell you about your application's performance. Within all of these things, we have inclusive versus exclusive measurements. For our exclusive measurement, you get you get the time just for the region of interest. For inclusive duration, you get the time for the region of interest and any subchildren. For example, here, the exclusive duration for this function foo is just the time that is spent in regions of the code that are directly within the scope of this function, and does not include the time that's spent in a call to some other function. But inclusive duration includes the time that is spent in the timer and any of its children. And then sort of finally, the last type of thing that we can measure are direct observation events. These are events that happen at a particular time in your application, but that don't represent entry or exit to a function or something like that, that naturally is a region of code or a region of execution space with a definite start and end. These include things like, for example, heap memory consumed at a particular point is an example of something that we can sort of periodically sample and save into a trace, but that is not necessarily associated with a particular entry and exit to a function. And so given sort of all of these sorts of things that we are capable of monitoring in Tau, sort of the central sort of high-level thing that we want to keep in mind is that we want to focus our measurements, given that there are all these trade-offs between how much time does it take to, what is the overhead of collecting it, what is the overhead of storing all of the data. We want to measure what matters. For example, if our file I/O, for example, if our file I/O is performing poorly, then that tends to be a dominating factor in resulting in poor performance of an application. So we would tend to want to sort of do a focused instrumentation to look there first, and then if we determine that there is a problem in that area, focus optimization there before we then go on and look at measures of communication, things like time spent in MPI collectives. We then want to go and look at memory, such as counters for cache utilization and memory bandwidth utilization. And then finally, look at compute-related optimizations like code vectorization. So we want to sort of go through an iterative process of repeatedly applying these steps until we have reached a point where the performance is about what we want. So now I'm going to sort of go over a high-level overview of how we can use tau to measure these sorts of things. And then I'll go into some more detailed examples of how you might run some of these things on the ALCF systems. So tau itself is an integrated toolkit for performance problem solving. It supports all of the different types of measurements that I mentioned, direct and indirect measurements, profiles of different types, traces of different types, is free, open source under the BSD license, is available on all HPC platforms that we are aware of, and some non-HPC platforms as well. Our goal with tau is that if there is an HPC system, if there is a programming language, if there is a framework that you're using for communication, then we want tau to support it. So we support a very wide array of different technologies, and if there's anything that you are interested in that we don't support, then we want to support it. So you should let us know about that. So tau is intended to be a sort of universal tool that is capable of performing any performance measurement that you care to do, including not just CPU-centric events, but data about file I/O, data about communication, data about memory utilization, and to do so with minimal overhead and with configurable overhead, so that you can choose the trade-off between precision and overhead yourself according to your specific needs. So tau is sort of split into three components. We have instrumentation, measurement, and analysis support. Within instrumentation, we can do source instrumentation of C, C++, Fortran, UPC, and some miscellaneous other languages in the compiled space. We have support for Python code, for Java code. We can operate also in a library interposition mode, for example, where we provide wrappers around communication libraries such as MPI, which you can you can interpose Tau's wrapper between your application and the underlying MPI layer in order to collect information about that. We support link time optimization, link time instrumentation, so that we can load these various wrappers either dynamically or statically during link time. And we support static and dynamic binary rewriting if you have, for example, an executable that you don't have the source code conveniently available for. We can do profiling, we can do tracing, we store metadata with profiling and tracing events to associate context back with that. We support events for various communication events, as well as events for GPUs. If you're using CUDA, we can time those kernels and collect that. And then on the analysis side, we provide a set of analysis and visualization tools, such as Paraprof, which provides 2D and 3D visualization of performance data data, Jumpshot, which provides visualization of traces, and also a tool called SOS, which provides for online analysis of tools, so that you can have sort of data as your application is running. You can have data streaming into SOS for analysis or visualization to run while your application is running, which can then feed back into your application to do, for example, online auto tuning or something like that. In terms of instrumentation, the thing that we have to do in order to instrument is to add probes into your application through any of the different mechanisms that I talked about, and then run your application to actually gather the data based on the instrumentation probes that were inserted, and then take that and visualize the data that we get out of this. So the sorts of questions that Tau can answer, the very basic question that you can answer is how much time did you spend in a particular code region? And if you don't tell Tau anything else, this is what it will give you. It will tell you for each region of your code how much time in this example, exclusive time, was spent in a particular region of code. So in this example, we spent 95.243 seconds on mean across 1,024 nodes in MPI all-to-all, and 40.554 in dubwise MPI at a particular source file at a particular location. We can also use hardware performance counters to collect data. For example, we might request data on how many floating point instructions were executed within a particular code region, and that will then give us a visualization of, for each code region, how much time was, or sorry, not how much time, how many floating point instructions were executed. We might ask how many level 1 or level 2 cache misses occurred by measuring the L1 DCM hardware performance counter. We might ask how much memory does the code use, and there's different ways that we might ask this question. So for example, we might ask what is the high water mark, or what is the largest amount of memory that was allocated at some particular time. We might ask how much memory in total was allocated throughout the execution of the program. We might ask how many bytes were allocated or deallocated within particular functions of our application. We might ask how much time is spent in MPI collectives. What are the sizes of the messages in total and on average, either for the application as a whole or for particular code regions. And we might present this data using a 3D visualization. For example, in this case, we have sort of the threads and ranks along one axis and different functions along the other axis, so that we can see where hotspots are across a large application that's running in, for example, MPI. We might visualize MPI communication directly. So, for example, there's an option, Taucom matrix, that will cause it to collect the volume and number of communications within MPI on the basis of sender and receiver. So, for example, in this case, there's sort of a large volume sort of communication along sort of near diagonal, which represents sort of communication to close neighbors of a largest volume, and sort of falling off as you become more distant. We can visualize on the basis of some topology that you provide externally. This is either a topology representing the physical layout, for example, of the machine on a network, or a topology internal to the domain of your application. And we can look at how routines scale as you increase the application size. So, for example, in this example here, we do a scaling study. We run the same application at varying numbers of ranks, and then the shaded regions up here represent individual functions. These are the top 10 functions in terms of time. And so, for example, we can see that as this application increases in number of processors as we scale up, we are spending an increasing proportion of the total runtime in MPI wait all and in write save file, indicating and sort of the reason for that in this particular application is that all of the data ends up getting sent back to rank 0 in order to be written out. So we have a larger volume of data being written out, and then all of the other nodes are waiting for node 0 to actually get around to finishing that. And so the scaling behavior of individual functions can tell you where you want to focus your optimization. And then in addition to this sort of proportionate view, we can also just look at this in terms of absolute time spent in different functions as we scale the number of MPI ranks. And then we can collect traces and look at when events occur during an application run. Okay, so sort of now we've gone over the basics of concepts behind performance analysis, measurements, and the basic functionality of tau. And so now I'll go into how you actually use this. So on Theta, tau is pre-installed in /soft/perf/tools/tau, and there are modules available for a number of recent versions of tau. So if you do module load tau /2.27.2, then you'll get the most recent version of tau loaded into your environment. You can also build tau yourself relatively easily in your own space in the file system. And the reason that you might want to do that is something that's a little bit unusual about tau. So in most Unix software, if I run the configure script and I pass in some arguments and then do make install, and then I run configure again with a different set of arguments and do make install, then what I would do is I would overwrite the first install with the second install. And that is not how tau works, and I think this confuses a lot of new users to tau. In tau, those two configurations end up getting installed side by side with different names. And the reason for that is that in tau, because we're very concerned with overhead, a lot of features are enabled at compile time rather than runtime, so that, for example, at the entry and exit to every function, we aren't having to go through a gigantic list of possible features and check whether you've enabled all of them, which adds a bunch of overtime, when you could instead just use a particular tau library that has those features permanently enabled or permanently disabled. So as I said, so to reduce overhead, a lot of the features are enabled at compile time rather than runtime, which means that you are likely going to need a bunch of different configurations of tau for different uses, depending on what options that you want. There's a few options that should generally always be used, such as BFD equals download and unwind equals download. And then other options that are very commonly used are specifying the particular compiler that you're using and enabling support for MPI and different threading environments like Pthread and OpenMP, enabling support for CUDA. So you might run configure with several different sets of options and install them all side by side, and then at compile or runtime choose the one that you want. The way that these are chosen at runtime is through a set of make files. So for every different configuration of tau that you configure, you will get a file in tau's home directory, and then in a file that indicates the architecture that it's built for. In Theta's case, that's Cray CNL, Cray Compute Node Linux. And then we have makefile.tau, and then a series of options that indicate what the options were when you compiled tau. And then when you're using tau's compile time instrumentation, there's an environment variable tau makefile that you set to be equal to the path to the makefile for the particular version of tau that you want to use. So in this case, this would be, for example, soft perf tools tau 2.27.2 / craycnl / lib / makefile.tau-intel-papi-mpi-pdt. And this says that among all of the versions of tau that are installed side by side in that directory, the one that you want to use is the one that uses Intel compilers that has support for PAPI, which lets you get hardware performance counter data, that has support for MPI applications, and then PDT indicates that it has support for source instrumentation of applications. So this is a package that has C, C++, Fortran parsers in it. And then there's sort of another mode in which you can use tau for everything other than source instrumentation, which is to use this wrapper script called tau-exec. Similarly, this takes an argument -T, and then it takes a set of tags that indicate which version of tau you want to use. And one thing that often trips up new users is that tau-exec in this list, it assumes MPI. If you don't specify a distributed communication library in here, it will stick MPI in there for you. And if what you mean is that you aren't using a distributed communication library at all, you have to say serial in here, and that can get a little confusing because serial doesn't necessarily mean single-threaded, so serial just means not MPI. So I could say, for example, serial, comma, pthread, and that just means not an MPI application, but it uses pthreads for intranode communication. There's parallelism. So a typical workflow in tau, we might start by doing some sampling to identify hotspots. We then might selectively instrument those hotspots using source instrumentation in order to get more accurate hardware performance counter data. We'll gather that data and then visualize the performance data using paraprof and visualize scaling data using the Perf Explorer tool that we have in tau. So the simplest way to get started with tau is, first of all, to make sure, so you have to make sure that you have a version of tau that is built appropriately for your application, and then just build your application as normally, except make it a dynamic executable and enable debug symbols. So tau's various wrappers don't work with static executables, which is the default with the Cray compiler wrapper scripts. So you do have to make sure that, for example, when you see cc-dynamic or ftn-dynamic in order to get a dynamic executable if you're using sampling support. You can then otherwise leave your compile process unchanged and then run the tau-exec script as the application that you're running through the launcher. It's very important that you put the tau-exec after AP run and the arguments to AP run, or you will end up sampling the performance of AP run itself on the mom node rather than of your application running on the compute node. Our other major option here is that we can insert tau API calls automatically. Here, we replace our calls to the compiler. For example, so if we were using CC and FTN without tau, we build a configuration of tau with the PDT library, and then we set the tau makefile environment variable to specify the version of tau that we're going to use, and then we replace the compiler with a call to tau's compiler wrappers. So there's tau underscore cc.sh for C, tau underscore cxx.sh for C++, and tau underscore f90.sh for Fortran. That will parse your source files and generate new versions of them that have calls to start and stop tau timers at the beginning and end of each function. There's a bunch of different options that you can specify for the compiler wrappers. The major ones that you might be interested in are optcomp_inst. This basically says that you don't, instead of parsing your source code and modifying it, you want it to compile your code normally, but then have the compiler itself insert calls at the beginning and end of every function. This can help if you have if you have some source code that for whatever reason is not parsable by tau's parsers. This can let you get around that problem. Another really useful option is opt_keep files. This keeps around in your source directory the instrumented versions of the files, so that, for example, if you want to manually instrument a code, you can do this and you can see what the source instrumenter is actually inserting into your code, and you can sort of use that to learn how to use tau's API manually if there's a region of code that is not a function that you want to insert calls to do. So once we're either executing an application that has been instrumented at compile time with tau, or an application that is being instrumented through sampling or library wrapping using the tau exec wrapper script, there are a number of runtime environment variables that we can set to control how tau's what type of data tau records. For example, if we set the environment variable tau trace to 1, it will record a trace instead of a profile. If we set tau call path to 1, it will record a call path profile instead of a flat profile. If we set tau com matrix to 1, it will generate a communication matrix of the type that I showed you before of what is the volume and number of communications between different ranks in your MPI application. And then there is a tau metrics option, which indicates the specific hardware performance counters that you're interested in capturing. So there are a whole set of hardware performance counters that are available on modern hardware, particularly with respect to cache behavior of the branch predictor, and memory resources, floating point instructions, the sorts of things. Tau collects hardware performance counter data through another open source package called PAPI. PAPI provides a number of tools that you would use together with tau in order to figure out what's available on your particular system. So PAPI, there's the main command line tool that you use to do this is called PAPI avail. When you run PAPI avail, it will display a list of information about your hardware. The important thing to look at here is the number of hardware counters. So for example, in this case, the number of hardware counters is 7. That means that there are basically 7 fields in the configuration registers for the processor that can store the identities of the hardware performance counters that you want to capture. And so that sort of sets a limit of the number of counters that you can accurately capture at the same time. There's also an option to do multiplex counters. So for example, this supports up to 32 multiplex counters. In that case, you are sort of rapidly switching back and forth, and so you're again trading off your precision for the ability to measure more at once. It will then list a set of counter names, and it will tell you whether they're available on your hardware and also whether they're derived, which means whether it consists of actually more than one hardware performance counter internally. And so you run this to figure out what it is possible to monitor on your particular hardware. Again, it's important that you run this on the compute node and not the mom node or the login node, because those are typically different processor families and they do not necessarily have the same hardware performance counters available. You can give the -E option to PAPI avail, and that will give you a description of, for a derived metric, it will tell you what are the underlying hardware counters that it's actually looking at and what the number of them are. So that's important for knowing, for example, like this one here takes up 2 native events. So that would consume 2 of the 7 hardware performance counter slots that are available on this particular processor. There's another tool called PAPI native avail, which will, rather than printing out sort of these high-level timers, it will print out absolutely every single hardware performance counter that your processor is capable of collecting. This is very, very long, so I recommend redirecting the output of this into a file for looking at it later. And then a very important tool that you can use for this is called PAPI Event Chooser. And PAPI Event Chooser helps you deal with the fact that not all hardware performance counters can be monitored simultaneously. So you might have a pair of hardware performance counters that are incompatible with one another. And PAPI Event Chooser lets you specify a hardware performance counter that you're interested in capturing, and it will give you a list of the hardware performance counters that are compatible with the one or multiple ones that you have indicated. If you want to capture hardware performance counters that are incompatible, you will have to do so over, well, you can use multiplexing if you want to make that trade-off, but typically you would have to capture that over multiple runs of your application. And this can take both the preset and native PAPI counters. So sort of to summarize this section of the talk, the general tau workflow is that we might start by using sampling to determine what to look at more closely. We can use Paraprof to store this data, to visualize the data. Once we figure out what we want to look at, we might use selective compiler instrumentation to insert calls to tau around specific code regions. We will use PAPI to look at hardware performance counters. We'll use the Paraprof tool again to look at that. So now I'm going to I'm going to demonstrate some of these tools for you. I'm running this demo. I'm running on my individual laptop, but once I'm done with the demo, then I'll go back and I'll give you instructions for running on Theta specifically. So on my system here, I have an installation of tau, and this installation has a whole bunch of different configurations of tau installed. And if I look in my tau library directory, I can see that I have a bunch of tau make files for. Okay, so I have a bunch of different versions of tau installed, and I'm going to go look at. I have just a simple MPI and Pthread matrix multiplication code here. It's one of the example codes that's included with tau, and so. I'm going to start by compiling this normally. So on the particular installation that I have here, I use MPI CC to carry out the compilation script. On Theta, you would use just CC, and I'll add some compile this with the MPI and Pthreads support, and I'll add debug symbols so that this will work with sampling. And I will compile a version of this. And if I run this just on my laptop normally, it will run for a few seconds and then tell me that it is done. And so that's just an totally uninstrumented application. I can then, so after my application launcher, I can say that that I want to run this through Tau, and I specify a particular version of Tau that I'm interested in using here. So I want this is an MPI application, so I want an MPI version. It's a Pthread application, so I want Pthread. Maybe I'm interested in hardware performance counters, so I also want PAPI to be enabled. And I'll then say that I want event-based sampling to be used in this application. So this will run as before for a few seconds, and then once it is done, I now have in this directory a bunch of profile files that correspond to the different ranks and the threads within those ranks of this application that I just ran. There's a tool called pprof, which I can run from the command line, which will show the performance data on the command line. And then there's paraprof. There's paraprof, which is our visualization tool. For example, we can click on a particular node and thread and bring up the time that was spent in different functions for this application. The timer called .tau application is the application as a whole, and then, for example, we can see that 8 seconds of the execution time was spent in the function called compute, and then 4 seconds was spent in a function called compute interchange. So we might be interested in collecting hardware performance counter data on those functions. So for this, we'll do we'll get rid of these profile files, and now we'll build a different version of this. This time, I'm going to use the Tau's compiler wrapper. So instead of MPICC, I say taocc.sh, but leave everything else the same. This is going to parse my source files, insert into the source files calls to start Tau timers, and so that gives me this Matmult inst program here, and I then can run that without Tau exec. That will run the version that has had instrumentation inserted manually inserted automatically into the code. Again, I get these profile files, and I can open up paraprof, and now this time I see very similar timings for compute and compute interchange, but this time I'm much more certain about them because I have inserted explicit calls to start and stop a timer around those specific functions. Now these are just sort of a naive matrix multiplication, and one of them, the one that takes a lot of time, has an order of the loops that is inefficient for the cache, but maybe we don't know that and we want to discover that. So we can run PAPI avail, and we can find out what hardware performance counters are available on our system. So for example, I'll set Tau metrics to be time, so I still want to capture the time data, and I also want to capture the number of level 1 cache data cache misses. I'll get rid of these profile files, and I'll run the application again. And I now have these directories multi-time and multi-PAPI L1 DCM that contain profile files for each of those metrics. If I run paraprof now, then I can go in here and I can select thread, and we can see the timing data like before. But I can also go in and I can say that I want to see the number of level 1 data cache misses that occurred inside those functions. And so here we can see that the number of level 1 data 1 cache misses that occurred in the function named compute is far greater than the number that occurred in compute interchange. Another thing we can do, for example, we can capture both PAPI L1 DCM data cache misses and PAPI L1 DCA data cache accesses, take the ratio of those, and then we have a level 1 data cache miss rate. Similar with the other things we can capture, use floating point operation counters to capture flop rates for applications and so on. So that's sort of an example of sort of some of the basics on how you might use Tau. And now I'll with my remaining time, I'll briefly run through some experiments that you can run on your own during the hands-on time if you're interested in learning more about Tau, to learn more about how to use it in some different scenarios. So for this, there's a series of exercises with source code and some pre-collected data for use with the analysis tools that is available at this URL. And you should be able to download the slides from the workshop website and get the link through there as well. So the first example that I would have you do if you're interested in learning about Tau is basically just to repeat what I just did in the live demo, but on Theta. My recommendation for this is that you start by you build your own Tau rather than using the Tau that is pre-installed, because it is likely that, if you become a heavy Tau user, that you are going to run into some configuration you need that is not pre-installed, and rather than bothering system administrators to get it installed, it's often a lot easier to just install it yourself, since Tau is not particularly difficult to install. So my initial instructions, basically you download PDT, which is our source parsing tool, extract and configure and install that. By default, it will install sort of directly into its source directory. So this is really easy to build in your own home or project directory on whatever system. You do not need any sort of administrative privileges. You then download Tau. And so for this example of the C matrix multiplication code, which uses MPI and Pthreads, what we want to do for Theta is build a version of this that first of all, we want BFD equals download, automated equals download. We always want that for any configuration of Tau. We want to build this for the compute node Linux. So we want to cross-compile this for the backend node. You want to give this the path to the PDT that you installed in the first part. Tell it the compiler that PDT used, because PDT is built for the front-end nodes, not the back-end nodes. And then we tell it that we want a configuration that works with MPI and Pthread. We install that, and we add our Tau's cracnl/bin directory to your path. You're then set up to use that. So if you download the package that I mentioned earlier, this has a series of directories in it. One of them is called 01_matmult.c. This has a make file in it that will build the matrix multiplication example with a compiler of your choice. So you, when you run this install step, at the very end of the install step, it will print out a path to your make file. You set your Tau make file environment variable to that. You run make with the Tau compiler wrapper script in place of your actual compiler. Then we just start an interactive session on the system and submit a job with AP run with this source instrumented version of Matmult. You'll do, if you look in your current directory, you'll see that there are profile files for each of the ranks that executed. We can, there's an option in paraprof-pack that will sort of zip all of those profile files together into one file for convenient transfer. I would recommend I would generally recommend, if you're going to use Paraprof, that you copy those to a local system rather than try and use X forwarding to view this over remote connection, although that is a possibility as well from a front-end node. Example 2 is very similar, but is a Fortran version of Matmult. The only thing that's different here is that instead of using tau-cc.sh, which is the C compiler wrapper, use tau-f90, which is the Fortran compiler wrapper. This, again, will parse your source code, generate your instrumented version, link that against the tau libraries, and then you run that sort of as normal through AP run, and then you can pack up your data, copy that to your local system, view the data in Paraprof. So for each of these, the basic workflow is choose your tau make file, use your compiler wrapper script, execute your application, analyze your performance data. Another application that you can do is, so tau also has support for Python. So for example, I have a Python application here. And tau has a Python wrapper, which is tau_Python. This takes the same kinds of arguments as tau exec does, but I wasn't on set tau metrics. So this will generate a profile file, which we can view in Paraprof, and this will show. This is such a short-running application that sort of the Python interpreter startup time is actually the dominating factor. The actual application code is this tiny green line right here. But for a longer-running application, you'll see things in there. We can also have a trace of this application saved, so I can do. I can look at this in the slog trace viewer. So we can see again here, most of this is actually just startup time in the interpreter. We can see the sort of application is split into, there's this find module phase where it's loading the initial module. It's compiling the Python code to Python bytecode, then actually executing it. This over here is the actual function in the application, and this at the end it prints the result. This section here is loading different Python modules that are imported by the application. So for this, you'll build a Python configuration that uses you'll build a tau configuration that uses Python. So you'll load a particular version of Python. You'll build you'll configure tau with -Python. You'll install that. Now, one thing that's very important about this is that this is not portable across Python versions. This is Python 3.6. You can only use this tau with Python 3.6. So make sure that you have that loaded in your compile environment and your runtime environment. If you use a different Python version, it will probably crash. So we have an example Python code here that's a simple chemical transport model, which is in the 03 FIXEDGRID.py directory in the example code. We can generate, for example, a call path profile to that. This is not a distributed application, so I'll run this on one node. We'll say serial since it's not MPI. We'll run this, and then just as before, you can use all of the tools to view the performance of that. In Paraprof, you can left click on a node to see the exclusive time. You can also view inclusive time. You can view, if you're selecting call path data, you can sort of view this as a tree as well by right-clicking on one of these nodes and selecting that you want to view the call statistics table. You can view it as a call graph that shows you what functions call what functions. You can zoom in on that. You can set this up to be like colored by the amount of time that's spent in different functions. We can also capture a trace by just setting tau trace = 1 and then view that in Jumpshot like I showed you in the demo. When you're doing this stuff and like setting environment variables like this, make sure to unset them if you're doing something else within the same session and you no longer mean that. We can also take a Python MPI application and monitor that with tau. So this is the fourth example in the package that I pointed you to. So here we'll build a version of tau with both Python and MPI support with our Miniconda 3.6 loaded. We'll run this on say 4 ranks, and then we'll get 4 profile files out of that, one for each of the ranks. Since this is an MPI application, even though it's using MPI for Pi rather than MPI directly, we will get, for example, communication data that we can see. So we get all of the MPI calls in addition to the Python calls in this. We can set comm matrix and get a communication matrix to see who communicated with who. We can collect a trace, and the trace will have these lines that indicate an MPI communication occurred in them. And then another thing that we can do with this is we can load these profiles into a database and then look at a bunch of them at once. So we can use the Perf Explorer tool to run scaling studies so that we can see that this particular application does not scale very well, and we can look at the time breakdown for different functions as we increase the number of processors, so that we can investigate that and figure out why it doesn't scale well. And then for the last example that I'll have you try, we combine a whole bunch of stuff. We have tau with Python MPI for Pi, plus the Python code calls out to C code that uses OpenMP. So for this example, we'll build with Python, we'll build with MPI, and we'll build with the OpenMP tools interface, which lets us capture data from that. We'll compile the C code that gets called by the Python with the tau compiler wrapper to source instrument that code, and then we will dynamically instrument the OpenMP calls and the Python code itself, which will give us a thread on each rank for the Python code, and then for each of the OpenMP worker threads that was running, we get another thread that shows the work done there. So we can look at the Python, we can look at the MPI calls, and we can look at the OpenMP threads, which in this application, because the code runs for such a short period of time, they're almost always sitting idle waiting for work to be provided for them to do. So that can give you information on what you need to do to get more work into that application. So you can get tau from tau.uoregon.edu. That's also where you can get documentation. If you have any questions or problems, well, if you're still here, you can talk to me, but otherwise you can email support@paratools.com with any of your tau bug problems, any just usage questions, anything you want. Tau has been supported by grants from many different organizations, all of which we thank, and that is what I have for you, and I would be happy to answer any questions that you might have, either now or later during the workshop. Thank you. Special permissions to use tau with what? Hardware counters. In general, if what you're interested in are sort of like basic things like cache miss rates and that sort of stuff, then no, you don't need any special permissions. Where you do need special permissions is if you're interested in capturing things like uncore counter data, which is what you need in order to get things like memory bandwidth, then recent Linux kernels have a kernel flag called perf event paranoid, which by default is set to either 2 or 3, and that prevents you from accessing the uncore counters. If that's true, you'll need your system administrator for your system to set that to a less restrictive setting to give you access to that. We have generally found that most system administrators are willing to do that, although some are not. How do I handle zillions of libraries, external libraries? So you can so if you have a whole bunch of external libraries, so typically what we would probably recommend that you source instrument like the most important ones of them, and then for the rest of them just compile them with a debug flag and use sampling. So you can combine source instrumentation and sampling, so that like you get your really accurate data for the libraries that you particularly care about, and then if you still want data for the other ones, you can use sampling for those libraries. And you can just you can compile some of your libraries with tau, some of them without tau, and then launch the whole application through tau exec with -ebs. And it's smart enough to know that it should only sample in the ones that aren't source instrumented. That was so I said that Miniconda is the one that I tested and verified that it would use when I was testing these examples before giving them to you to make sure they would work. It doesn't mean unless that I haven't tested with that other Python. I can if you would like. I suspect that it probably will work. It's just that you have to make sure that you have that version loaded when you compile tau and when you run your application. You can't mix and match versions of Python. Right. So the does that Python only runs on the compute nodes? Yeah, that might. Yeah, if the Python executable, it does try to. There's probably a way around that. So instead of saying -python, you can also say -python inc -python lib and like give it the paths to the Python version, because otherwise it actually tries to run Python to auto detect the paths. If you can't run the Python, you can provide the paths manually. That will probably work. Okay, thank you.